Hello and welcome to our third Thursday webinar. I am Tom Sandry, and today we're going to be talking about understanding insulation resistance testing. All right, let's get started. Now, in this webinar, we will be reviewing insulation and its properties along with basic causes of insulation degradation. We're going to be talking about, what is insulation and the properties of a dielectric? What causes insulation to degrade in the first place? How is insulation resistance measured? How does an insulation tester or megohmmeter operate? What are the types of tests that you can perform with an insulation test set? How do you obtain quality measurement results? Are there safety concerns when using an insulation resistance test set? So let's start with what is electrical insulation. Now, electrical insulation is a non-conducting material that provides electrical isolation of two parts at different electrical potentials. To accomplish this, an insulator must meet two primary requirements. It must have an electrical resistance and a dielectric strength that is sufficient for the given application. The secondary requirements relate to thermal and mechanical properties, and occasionally tertiary requirements relating to dielectric loss and dielectric constant must also be observed. A complementary requirement is that the required properties not deteriorate in each environment and desired lifetime. Now, electrical insulation is generally a vital factor in both the technical and economic feasibility of complex electrical power systems. The generation, transmission, and distribution of electrical power depends critically upon the performance of electric insulation. Now, the basic difference between a conductor and an insulator or dielectric is that free charge has high mobility on and in a conductor, whereas free charge has little or no mobility on or in a dielectric. Dielectric strength is a measure of the electric stress required to abruptly move substantial charge on or through a dielectric. It deteriorates with the ingress of water and with elevated temperature. For high voltage applications, dielectric strength is the most important single property of the insulation. Insulation resistance is a measure of how much current will be drained away from the conductor through the bulk or along the surface of the dielectric. Now, types of insulation. All insulators may be classified as either a solid or a liquid. Solid insulation is further divided into, is it flexible or rigid type? Flexible insulation is generally thermoplastic and commonly used for electric power cables. Thermoplastic are initially soft and can be extruded by using only pressure. Examples of these extruded dielectrics include polyethylene, or PE, cross-linked polyethylene, or XLPE, and ethylene propylene rubber, or EPR. Now, cellulose paper insulation is also used as an insulator. It is neither thermoplastic nor thermosetting. It is widely used in cables such as paper-insulated lead-covered cables, transformers, and rotating machinery in multi-layers and impregnated with oil. Now, rigid insulation includes glass, mica, epoxies, porcelain, alumina, and other ceramics. Rather than being used to insulate wires and cables, except for mica, these materials are used in equipment terminations, such as potheads, and as support insulators, such as in tension or compression, for overhead lines, whose primary dielectric is air. These rigid structures must be shock resistant, be relatively water impervious, and be able to endure corona discharges over their surfaces. Now, liquid, gases, and vacuum fall into the category of fluid insulation. For all these, the electrical structure must be such as to contain the fluid in the regions of high electric stress. Fluid insulators are used in very high power, high current devices where using solid insulation and a heat sink would be too bulky, or where a very large amount of waste heat must be removed from a relatively small area. Dielectric materials refer to non-conductors or insulators in which an electric field can be sustained with a minimum dissipation of power. Unlike metals, no electricity flows in dielectrics when they are placed in an electric field. Instead, dielectric polarization occurs. When a dielectric is placed in an electric field, electric charges do not flow through the material as they do in a conductor, but only slightly shift from their average equilibrium positions, causing dielectric polarization. This produces an internal electric field, reducing the overall electric field of the dielectric. Now, an important consideration for a dielectric material is its ability to support an electrostatic field while dissipating minimum energy in the form of heat. This dissipated heat or energy loss is known as dielectric loss. The lower the dielectric loss, the more effective the substance is as a dielectric material. Now, another consideration is the dielectric constant, which is the extent to which a substance concentrates the electrostatic lines of flux. Substances with a low dielectric constant include a perfect vacuum, dry air, and most pure dry gases, such as helium and nitrogen. Materials with moderate dielectric constants include ceramics, distilled water, paper, mica, polyethylene, and glass. Metal oxides, in general, have a high dielectric constant. Now, the differences between a dielectric versus an insulator. Dielectrics can develop an internal electric field which nullifies the externally applied voltage, while insulators do not develop an internal electric field. Dielectrics are easily polarized and can store charges. Insulators actively obstruct electricity. Dielectrics contain relatively weak bonds with atoms. Insulators contain strong covalent bonds. And finally, dielectrics are mainly used in capacitors, power cables, transformers, and resonator oscillators, while insulators are used in high voltage line systems and electrical appliances to prevent users from getting electric shocks. Now, let's move on and talk a little bit about what causes the insulation to degrade. We'll start first with electric stress. Insulation is designed for a particular application, obviously. Overvoltage and undervoltage cause abnormal stresses within the insulation, which can lead to cracking or delamination of the insulation. Now, we also have mechanical stresses at play. Mechanical damage, such as hitting a cable while digging a trench, is fairly obvious, but mechanical stresses also may occur from running a machine out of balance or frequent stops and starts. The resulting vibration from machine operation may cause defects within the insulation. Now, among the contributors of degradation, we also have chemical attack. Now, while you would expect insulation to be affected by corrosive vapors, dirt and oil can also operate to reduce the effectiveness of insulation. Thermal stress. Running a piece of machinery in excessively hot or cold conditions will cause overexpansion or contraction of the insulation, which might result in cracks and failures. However, thermal stresses are also incurred every time a machine is started or stopped. Unless the machine is designed for intermittent use, every start and stop will adversely affect the aging process of the insulation. Now, continuing on the subject of heat stress, heat dissipation is an important factor when considering ampacity. If heat cannot dissipate, the insulation begins to heat up and can lead the insulation into thermal runaway. For example, the thermal resistivity, or the rate that a specific material can resist the flow of heat, is different for each component of a cable and the medium around the cable, which can be ductwork or the natural environment, such as in direct buried applications. If the thermal resistivity of a material is low, then the heat can dissipate quickly, removing or displacing the heat away from, in this application, the cable. Now, let's talk also about some environmental contamination. Now, environmental contamination covers a multitude of agents ranging from moisture from processes to humidity on a muggy day, and it can even include items such as a rodent attack gnawing away at the insulation. Now, next, how is insulation resistance actually measured? Well, insulation resistance is measured with an insulation resistance test set, commonly referred to as a megohmmeter, and in some cases it kind of has the slang name of megger, although megger is actually a manufacturer, a company that manufactures insulation resistance test sets. Now, there are several manufacturers of insulation resistance test sets, such as Megger, AEMC Instruments, Fluke, and Metrel, just to mention a few manufacturers. Now, an insulation resistance tester is a portable instrument that provides a direct reading of insulation resistance in ohms, megohms, gigohms, or teraohms, regardless of the test voltage selected. For good insulation, the resistance usually reads in the megohms or higher ranges. An insulation resistance tester is essentially a high-range resistance meter or ohm meter with its own built-in DC generator. The instrument's generator, which can be hand-cranked, battery, or line-operated, develops a high DC voltage that causes several small currents to flow through and over surfaces of the insulation being tested. The total current is measured by the ohm meter, which has an analog indicating scale, a digital readout, or in many cases, both an analog and a digital readout. Now, some insulation resistance testers have 2 terminals, others have 3 terminals. As these are DC testers, Two of the terminals are the positive potential and the negative potential. The third, if present, is a guard. It does not have to be used, and many operators use insulation testers satisfactorily without ever employing the guard circuit. However, it affords the operator an extra function of diagnosis of equipment problems. The guard is a shunt circuit that diverts surface leakage current around the measurement function. If parallel leakage paths exist, a guard connection will eliminate those from the measurement and give a more precise reading of the actual leakage between the remaining elements, as we can kind of see in the graphic shown on the slide. Now, connecting the insulation tester. DC high potential testers and megohmmeters are fairly common test sets used by high voltage technicians and engineers. The basic operation for both a DC hipot and a megohmmeter is the same. A known DC voltage is applied across the insulation. The applied potential causes several small currents that flow through and over surfaces of the insulation being tested. The total current is then measured, and the result is displayed as either an ohmic value, or it can be displayed as the actual total current that is flowing. With modern insulating materials, there is little, if any, difference in the reading obtained regardless of which way the terminals of the test set are connected. However, did you know that it is industry standard to connect the positive lead to ground? In fact, the output polarity of DC high potential test sets are designed to be negative polarity, positive ground. The reason for this is that on older insulation, a little known phenomenon called electrodosmosis causes a lower insulation reading to be obtained with the positive terminal connected to the ground side of the insulation being tested. Now, since insulation testing is typically concerned with safety, maintenance, and/or troubleshooting, the worst case reading would be the one which yields the most relevant information. Also, negative polarity is preferred since water molecules are positive polarity and are attracted to the negative voltage, which gives a more comprehensive picture of insulation condition. Now, unlike DC high potential test sets, most megohmmeters on the market do not have fixed or permanently attached test leads. Rather, they provide a positive and a negative test terminal. Now, in some of the older instruments, the positive terminal was actually referred to as the ground, and the negative terminal was referred to as the line terminal. Now, if the user doesn't know any better or doesn't read the manual or the literature, they may be likely to use the positive polarity connected to the line side of the circuit. Now, as stated earlier, with most modern insulation, it makes little difference. But with older insulation and a lot of wound devices, motors and transformers as such, it does matter when trying to obtain consistent readings. All right, let's move on and talk about the components of the test current. Now, if we apply a test voltage across a piece of insulation, then by measuring the resulting current and applying Ohm's law, which simply states resistance equals voltage divided by current, we can calculate the insulation resistance, or the resistance of the insulation. Unfortunately, more than one current flows, which tends to complicate matters. The total current that flows during an insulation resistance test is made up of three main components. First, we have what is known as the capacitive charging current, I sub C. The current required to charge the capacitance of the insulation being tested. Now, this current is initially large but relatively short-lived, dropping exponentially to a value close to zero as the item under test is charged. Insulating materials become charged in the same way as a dielectric in a capacitor. Next, we have what's known as the absorption or the polarization current, I sub A. Absorption current, which is the current that is being drawn into the insulation by the polarizing of the electrons, it is initially high but drops over time at a rate slightly slower than the charging current. Now, for those of you who have done insulation resistance testing on various specimens, you may have noticed a phenomena with the insulation resistance test set that when you connect it to the device under test and you hit test, initially you'll get a insulation resistance reading. But over time, for instance over the next 60 seconds, you notice that the insulation resistance continually climbs. Now, to an untrained eye, one may draw a conclusion that, my goodness, the longer that potential is applied to an insulator, the stronger the insulation becomes. But that's really not true. What we are actually observing is these time-based currents, capacitive charging and absorption or polarization. And since current and resistance have an inverse relationship, as the charging current and the absorption current are flowing, resistance is therefore lower. As these time-based currents drop to zero, the insulation resistance goes up. And that is why, when you test, the insulation resistance is typically at some nominal value, and over a period of time, you see insulation resistance grow. Now, this is also a very important fact to understand when testing large capacitive devices, such as medium voltage cables of substantial length, or for instance, large motor stators, transformers, or generators. These large bulk insulating systems have a lot of capacitance associated with it. So the old rule of thumb of 1 minute document the reading does not always apply in these situations. It may take much longer than 60 seconds to overcome the charging current and the absorption current. In many cases, it can take several minutes before you actually get a stabilized reading on the megohmmeter. So watch for that when testing devices with large capacitance. All right, let's talk about the other currents that flow. We also have the conduction or leakage current. Now, the conduction or leakage current, which is the small steady state current that divides into two parts: the conduction path through the insulation and the current flowing over the surface of the insulation. This is the current that we are interested in and that we document during an insulation resistance test. All right, when connecting to a single conductor cable for the purpose of measuring the insulation resistance of conductor to ground, we make the following connections. We connect the positive, or on older instruments referred to as the earth terminal, of the megohmmeter to the cable's sheath or its metallic neutral. Next, we connect the negative, or on the older insulation resistance test sets, this will be referred to as the line terminal. We connect the negative to the conductor of the cable under test. Now, for a multi-conductor cable, where we have multiple conductors in the core, we can use a combination of connections depending upon which aspects of the insulation we want to measure. So, first, if we want to measure one conductor to all of the other, let's just say metallic surfaces, we can jumper two of the internal conductors together. We would jumper those conductors to the metallic shield. We would then connect the positive lead to the metallic shield, the negative potential lead to the conductor of interest, and now we are measuring the leakage current of that conductor of interest to all of the other conductive surfaces within that three-core cable. Now, we may wish to do some isolation, where we only want to measure one conductor to earth without the influence of the leakage current flowing to the other conductors. So to do this, we would once again short out the two conductors that are not involved in the test. We would connect the positive lead to the metallic shield, the negative lead to the conductor of interest, and we would use the guard terminal on the two conductors that are not of interest. So now any leakage current flowing to those conductors bypasses the measurement circuit through the guard circuit, and we are only measuring the leakage current of the conductor of interest to the metallic shield. All right, another possibility is we want to measure one conductor to the other conductors minus the ground. So now we're only interested in the current that is flowing from the conductor of interest to the other conductors, but we are no longer interested in the current that is flowing from the conductor of interest to the shield. So, once again, we jumper the two conductors. We connect the positive lead to the two conductors. We connect the negative lead to the conductor of interest, and we connect the guard terminal to the metallic shield. So any current flowing to the metallic shield bypasses the measurement circuit. It does not contribute to the measurement, and we are only now measuring the current that is flowing from the conductor of interest to the other conductors in the tri-core cable. All right, now let's take a look at testing of a transformer. So here in the graphic, we're kind of looking at an aerial looking down at the top terminals of a transformer. Now again, there are various measurements that we can apply here and isolate different sections of the complex insulating system inside the transformer. So the first one we'll look at is high voltage winding to low voltage winding and ground. So in essence, we're going to measure the leakage current going from the high voltage windings to the low voltage windings and the leakage current flowing to ground or to the chassis or frame tank of the transformer. Now, for safety, we jumper and short out the windings. The reason why we do this as a safety initiative is the windings are large coils. They have inductance. Now, as you apply a potential and you begin energizing, a magnetic field begins to build across the inductor. Okay? Now, this in itself is not necessarily dangerous because it is DC being applied, but we are creating a magnetic field around that winding. Now, in order to have induction, we have to have relative movement. That magnetic field has to move and cut across the secondary windings in order to cause induction. So during the charging portion of the test, the magnetic field is being formed. Nothing is being induced. However, when you turn the test set off after completing the measurement, that magnetic field is going to collapse, causing movement and cutting across the secondary windings, causing an induction onto the secondary. Therefore, for safety purposes, we jumper out the H terminals and we jumper out the X terminals. Effectively, by shorting out the winding, we remove the inductance and we then eliminate the hazard of inducing onto the secondary. Now, continuing on with this measurement of high voltage winding to low voltage winding and ground, we will next go ahead and connect the positive terminal to the X windings, the negative terminal to the H windings, and notice how the X windings are also, the XO is tied to the chassis or ground of the transformer tank. So in this configuration, we will now measure any leakage current that is going from high to low and any leakage current that is going to ground. Now, in our next configuration, let's say we want to measure high voltage winding to ground with the low voltage winding to guard. So in essence, in this setup, we're only interested in what is the leakage current that is flowing from the high voltage winding to ground, and we don't want the contribution of any current that is flowing from the low voltage winding. So, once again for safety, we short out the windings. Here we are going to leave the XO isolated from the chassis ground. We are going to connect the megohmmeter, positive lead, to the chassis ground of the transformer, the negative lead to the H windings because we want to measure voltage from the windings to ground, and we don't want the contribution of the low voltage windings to affect our measurement. So in this configuration, we are now isolating and only looking at the leakage current going from the high windings to ground or to the chassis of the transformer. All right, our next one, low voltage winding to high voltage winding and ground. So this is going to be similar in configuration to when we did the high voltage winding to low voltage winding and ground. Once again, we're going to short out the windings. We are going to jumper the high windings to the chassis ground. We are going to short out the windings on the low voltage side. Positive test lead would get connected to the high windings, negative lead to the X windings. And in this configuration, we are now measuring the leakage current going from the low voltage windings to the high voltage windings and the leakage current going from the low voltage windings to ground. All right, now low voltage windings to ground and high voltage windings being guarded out of the circuit. So again, we short them out for safety. We connect the positive lead to the chassis ground of the transformer, the negative lead to the low voltage windings, and the guard circuit to the high voltage windings. So now we are only measuring the leakage current going from the low voltage windings to ground, and any leakage current that is flowing from the low voltage windings to the high voltage windings are being bypassed from the measurement circuit through the guard circuit. So they are not contributing to our final reading. All right, and high voltage winding to low voltage winding. Once again, we short out the windings. Positive lead to the low voltage windings, negative lead to the high voltage windings, and now we are measuring the leakage current going from the high voltage windings through to the low voltage windings. All right, let's move on now from transformers and let's take a look at AC motors. Now, it is recommended when feasible that each phase be isolated and tested separately. Separate testing allows a comparison to be made between phases. When one phase is tested, the other two phases should be grounded to the same ground as the stator core or rotor body. Now, when testing all phases simultaneously, only the insulation to ground is tested and no test is made of the phase-to-phase insulation. The phase-to-phase insulation is tested only when one phase is energized and the other phases are grounded. The connection leads, bushing riggings, cables, switches, capacitors, surge arresters, voltage transformers, and other external equipment may greatly influence the insulation resistance reading. It is recommended that measurements of the insulation resistance be made with all external equipment disconnected and grounded. In all cases, a common ground should be used to avoid any undesirable effects on the test results due to stray losses in the ground circuit. And as far as our connections are now concerned, we ground the conductors, as mentioned, that are not part of the test, and we ground them to the rotor or stator chassis. We connect the positive lead to the ground, the negative lead to the conductor or phase of interest, and perform our insulation resistance test. And then we would basically repeat this hookup for the other two remaining phases. All right, now let's take a look at the tests that are performed on a circuit breaker, typical tests that are performed. We have tests that are performed with the breaker in the open position. We also have tests that are performed with the breaker in the closed position. For instance, with the breaker open, we can measure the line to ground and the load to ground. This would be a combination of 6 measurements for line to ground on phase A, B, and C, and then load to ground on phase A, B, and C. We are basically looking at the backboard and the stabs to ground. Now, also with the breaker open, we can measure line stab to load stab. Okay, these would basically be 3 measurements, one for each phase, the line stab to the load stab. And remember, the breaker is in the open position here. Here we are now measuring the insulation of the arc chute or the vacuum bottle. Now, with the breaker in the closed position, we can measure line stab to ground. And again, we're typically looking at the backboard and the stab to ground insulation. Also, we can take a look at the phase-to-phase insulation resistance. So, let's go take a look at some very simplistic connections. So, line and load stabs to ground. The breaker, again, is in the open position, and there will be a total of 6 measurements. So here, for instance, on phase A, line to ground. Phase A, load to ground. Phase B, line to ground, load to ground. Phase C, line to ground, and load to ground. Now, line stabs to load stabs. Remember, the breaker is in the open position, so we are measuring the insulation resistance across that open. And for phase A, our hookup configuration is shown. phase B, and finally phase C. Now, closing the breaker contacts, we can now do line stab to ground. So for instance, for A phase, B phase, and C phase. And finally, phase-to-phase measurements. So we can measure A to B, B to C, and C to A. All right, let's move on now and let's talk about different types of tests that we can perform. Probably the most common and most known is the spot reading. The spot reading test is the simplest of all the insulation tests. The test voltage is applied for a short, specific period, typically 60 seconds, as usually any capacitive charging current will have decayed by this time. And then the reading, when it is stabilized, the reading is taken or documented. However, caution, as I mentioned earlier, large capacitive devices such as long lengths of medium voltage cable, large motor stators, etc., these may take much longer than 60 seconds to go through their charging, and you would need to wait until the reading stabilizes or until the charging and absorption currents have depleted before the reading was stabilized and you can document your insulation resistance spot reading. Now, the reading can then be compared to the minimum insulation specifications. Spot readings can be performed as part of an inspection or as part of troubleshooting and can be used as a simple go, no-go, good or bad indicator of the insulation. Spot readings can also be trended against previously obtained values. However, as we're going to talk in a little bit, if you are going to trend, temperature has a big effect on the insulation resistance readings. So utilizing a correction factor so that we can correct for temperature will be important if we are going to do trending of these measurements. So, interpreting the data. If the insulation resistance reading was high and it is increased or remained steady during the test, the insulation is generally good. Current decreases as insulation resistance increases. So again, as the charging current depletes, as the absorption current depletes, the insulation resistance climbs to its final value, showing just the leakage current going through the insulator. If the insulation resistance reading decreases during the test, the insulation of the cable or device under test is probably wet or otherwise in a bad or dubious condition. If the final value is low or the current that we're measuring remains high, the insulation of the cable is in poor condition, or insulation of the device under test is in poor condition. Now, as I mentioned before, if we are going to trend our results, temperature will have an effect on the insulation resistance measurement. So for trending purposes, we would need to correct for temperature in order to have a meaningful trend. All right, let's now talk a little bit about a test called Polarization Index and dielectric absorption. Now, a valuable property of insulation, but one that must be understood, is that it charges during the course of a test. The polar DC field applied by the tester causes realignment of the insulating materials on the molecular level as dipoles orient themselves with the field. Now, this movement of charge constitutes, of course, a current. Its value as a diagnostic indicator is based on two opposing factors. The current dies away as the structure reaches its final orientation, while leakage, promoted by deterioration, passes a comparatively large constant current. The net result is that with good insulation, leakage current is relatively small, and resistance rises dramatically as charging goes to completion. This changing resistance is exactly what an experienced technician wants to see. Deteriorated insulation will pass relatively large amounts of leakage current at a constant rate for the applied voltage. This will flood out the charging effect, making the leakage current the more dominant of the currents flowing. Time resistance methods, as they are known, take advantage of this charging effect. Graphing the resistance reading at time intervals from initiation of the test yields a smooth rising curve for good insulation, but a flat graph for deteriorated or contaminated equipment. The ultimate simplification of this technique is represented by the popular Polarization Index, or PI, test, or the dielectric absorption tests, which require only two readings and a simple division. Performing the Polarization Index test, the 1 minute reading is divided into the 10-minute reading to provide a ratio. In dielectric absorption, the time values are typically 30 seconds and 60 seconds. Now, obviously, a low ratio indicates little to no change, hence poor insulation, while a high ratio indicates the opposite. References to typical PI values are common in the literature, which makes this test very easy and readily employed. Note that resistance readings alone are difficult to work with, as they may range from enormous values in new equipment down to a few megohms just before removal from service. A test like the Polarization Index is particularly useful because it can be performed on even the longest of cables, and it yields a self-contained evaluation based on relative readings rather than absolute values. So, here we would see kind of an example of a polarization index test being performed on a rotating machine. Again, we take readings at various time intervals and we graph them. And in the polarization index test, we then basically take the ratio of the 1 minute to the 10-minute reading. All right, another test that is occasionally done on devices is called the step voltage test. Now, since good insulation is resistive, an increase in test voltage will lead to an increase in current with a result that the resistance remains constant. So in essence, what we're saying is that as potential goes up, leakage current would go up, but the resistance should remain constant. The voltage and the current should go up proportionally. Any deviation from this could signify defective insulation. At lower test voltages, say 500 or 1,000 volts, it is quite possible that these defects might be unobserved. But as the voltage rises, we reach a point where ionization can take place within cracks or cavities, resulting in an increase in current and therefore a reduction in the insulation resistance. Note that it is not necessary to reach the design voltage of the insulation for these defects to become apparent, since we are simply looking for ionization in the defect. The step voltage test follows exactly this principle and can be employed usefully at voltages reaching 2,500 volts and upwards. The step voltage test may be employed as an undervoltage or overvoltage test. However, it must be remembered that an overvoltage test can lead to a catastrophic failure if insulation breaks down because high voltage test sets such as hipots have a lot of power available. An undervoltage test carried out by an insulation resistance test set has relatively little power available, and it is therefore far less likely to result in a destructive test. A recognized standard procedure is to increase voltage in 5 equal steps at 1-minute increments and record the final insulation resistance at each level. Any marked or unusual resistance reduction is an indication of incipient weakness in the insulation. All right, now let's take a look and talk a little bit about potential sources of errors in our measurements. Now, beware of using low-quality leads whose voltage rating is less than the test voltage that you're going to be using. It is extremely important that the only leakage currents during a measurement are those that are developed by the insulation that you are testing. If the leads themselves produce leakage, you may be measuring lead insulation resistance rather than the item that you are primarily interested in. Test leads should not be allowed to touch each other or any other object, since this will induce leakage paths. Sharp points at the test lead connections should be avoided, since this will encourage corona discharges. Now, another area that is sometimes misunderstood in readings when dealing with series and parallel circuits. Now, in a series circuit, resistances add. So R1 plus R2 plus R3 would provide the total resistance of the series circuit. But when resistors are placed in parallel, the voltage across the resistors is the same, but the current through each one is inversely proportional to its resistance. So in essence, the resistances add up as reciprocal values, as we see in the equation shown. Now, one area where this is important is when we are testing busway systems. So for instance, in an application where we are going to test multiple busway sections and then assemble the sections together to form the bus. Now, we are measuring phase to ground. Therefore, we are measuring parallel resistances. So, in the example that I laid out, let's say that we have 3 sections of a busway. And initially, for inspection, we're going to measure each individual section. So, we connect onto section 1, and let's say we get a measurement of 20 megohms. We connect onto section number 2, and let's say we get 10 megohms. And finally, we measure section 3, and perhaps we get another 20 megohms. So individually, separate pieces, we have 20 megohms, 10 megohms, and 20 megohms. Now we go ahead and we join the bus sections together to form the full busway, and we now, in final inspection of the completed assembly, we measure the insulation resistance phase to ground once again. What do you believe the final resistance value will come out to be? Well, remember, these are going to add as reciprocal values. Therefore, in order to get the final reading, we would take 1 divided by 20 plus 1 divided by 10 plus 1 divided by 20. That would give us 1 over 5. We take the reciprocal of that, and our total resistance of the new assembled busway system is going to be 5 megohms. So notice that when we add resistances in parallel, the final reading will always be less than the lowest section's insulation resistance value. All right, now let's talk a little bit about safety. When performing electrical testing, we are temporarily energizing the circuit with a test potential or voltage. The device under test is now energized and presents itself as an electric shock hazard. Energy control safe work practices must be followed to mitigate this hazard. Electrical shock approach boundaries must be established at both ends of a cable or a busway system in order to create a safe test area for workers. Also, an energized cable or busway system can create capacitive coupling to adjacent cables or phases. To prevent capacitive coupling, cable phases or bus bars that are not being energized or actively tested, they must be grounded. This will prevent any capacitive coupling onto those cables or those bus bars that are not actively being tested. Now let's talk a little bit about electric shock. Shock hazard is a source of possible injury or damage to health associated with current through the body caused by contact or approach to energized electrical conductors or circuit parts. It is current through the body that causes electric shock or, in the extreme, electrocution. The potential difference a person may contact between conductive parts of equipment or between equipment and ground is important because the voltage forces current through the body according to Ohm's law. Therefore, current through the body increases with lower body resistance and it increases with higher contact voltages. Now, let's take a look at effect on the human body. Now, a lot of this research on the effects of current in the human body was actually taken back in the 1960s by research conducted at the University of California in Berkeley. The maximum safe body current for short periods of time is given by Professor Dalziel's equation and is an inverse function of time, meaning higher currents are permitted for shorter periods of time, where in the equation we show that the maximum safe body current, I sub k, would equal a factor of body weight divided by the shock duration time. Now, taking a look at effects on the human body, we see that at 5 milliamps, and this is typically the charging current that most megohmmeters utilize. Somewhere between 3 to 5 milliamps would be the output current of most insulation resistance test sets. And we see that at 5 milliamps, it's a slight shock that is felt, not painful, but can be disturbing. Average individuals can let go. We don't have muscle contraction at this point, so most individuals can let go of the circuit. However, strong involuntary reactions to the shock in this range may lead to injuries. Now, as an information note, most high potential test sets will typically utilize currents of 100 to 300 milliamps of charging current. So if using a high potential test set, the output can be much more dangerous, where at the 100 milliamp level, ventricular fibrillation, uneven, uncoordinated pumping of the heart can occur. Muscular contraction and nerve damage begins to occur. Death becomes likely at these current levels. Now, energized circuits or circuit parts put out electrostatic fields. These fields are created by the voltage, and the two have a causal relationship, which means the higher the voltage, the greater the electrostatic field that is being produced. Any circuit interaction within these fields can lead to electric field induction, or also called capacitive coupling. So electric field induction is the process of generating voltages or currents to ground or both in a conductive object or electric circuit by means of time-varying electric fields. Now, since these fields have a causal relationship with voltage, approach boundaries for safety have the same relationship. The higher voltages require greater distances for safety. Now remember, you don't necessarily need to come in contact with those energized circuit parts for them to arc across and give you a shock. You just need to come within a certain distance and interact with that electrostatic field. So for safety, we have what are known as approach distances. In the NFPA 70E, one of these approach distances that is mentioned is called the limited approach, and it is a shock awareness boundary. So, limited approach, as defined by the 70E, it is an approach limit at a distance from an exposed energized electrical conductor or circuit part within which a shock hazard exists. This boundary is determined based on the nominal phase-to-phase voltage of the energized conductor or circuit part. Now, also in the NFPA 70E, they talk about what is called a restricted approach boundary. And once again, this is for shock awareness. So the restricted approach boundary is an approach limit at a distance from an exposed energized electrical conductor or circuit part within which there is an increased likelihood of electric shock due to electric arc over combined with inadvertent movement. This boundary is determined based on nominal phase-to-phase voltage of the energized conductor or circuit part. Now, in the NFPA 70E, they provide shock boundary tables. Here is an example of those tables. So we would see for AC applications, for instance, let's say I am going to be doing a test where my test set will be applying, let's say it's a high potential test set, and I'm going to be applying, maybe 10,000 volts of AC voltage to the device being tested. So here we would look at the voltage level. The limited approach boundary for 10 kV would be 5 foot, and the restricted boundary would be 2 foot 2 inches. These are the safety approach boundaries that we would need to establish in our work area when testing at these potential levels. Now, let's say I'm doing a 5 kV megohmmeter test. Well, megohmmeters, as we mentioned earlier, use DC. So for 5 kV DC, using the DC table, our limited approach would be 5 feet, and our restricted approach would be 1 foot 5 inches. And these would be the safety barriers that we would apply in our work area. Now, our safe work practices when applying any type of a test voltage to a specimen. Obtain and review up-to-date drawings and prints of the circuits to be tested. If up-to-date drawings and prints are not available, circuits need to be traced out and documented prior to any application of temporary voltage. Bottom line, you've got to know where the voltage is going. Temporary application of voltages cannot proceed until the circuit path, potential backfeeds, affected gear, and circuit access areas are known and factored into the shock hazard assessment, and temporary energy control safety plan. When applying voltage to a circuit, you must treat all parts as energized. You must establish the limited and restricted approach distances based on the applied voltage. When testing circuits, you must first verify where the voltage is going. As an example, verify both ends of a cable or a long busway system. You must 100% know the circuit paths prior to applying energy. Prior to the test, you must barricade all access points. In high traffic areas, barricades may not be sufficient to keep people out, and an attendant should watch all access points. Now, the current available from a megohmmeter is generally limited to only a few milliamps and presents relatively low hazard. However, the danger is not so much the output of the megohmmeter, but more the working environment. If the connected load is very capacitive in nature, this can provide very significant energy when charged to high voltage by the megohmmeter, and it can lead to a lethal discharge if the specimen is touched while charged. The circuit under test must be switched off, de-energized, isolated, and checked to be safe before insulation test connections are made. Test before touch every time without exception. After completing a test, capacitive currents must be completely discharged before disconnecting the test leads or handling the circuit. And closing out on that safety overview, that concludes our webinar for today. As always, thank you. We appreciate your attendance and participation in our Third Thursday webinars. As I always say, Matt and I do truly enjoy doing this program. We hope that you find value in these webinars, and we look forward to seeing you in our next webinar. But for now, how about we get to those questions and answers?